Hello. Today we're going to look at a very important concept, a method of finding antiderivatives called substitution. It is one of the most important methods of finding antiderivatives. It's the reverse of the chain rule, and it's used extensively. Now, some background. Before, with the chain rule, we had a function, capital F of x, which was a composition f of g of x, and its derivative, f prime of x, was f prime of g of x times g prime of x. Well, now we want to kind of reverse that process. Now, with substitution, mess in there. We want the antiderivative of something of the form f prime of g of x times g prime of x dx. And so what we do, we let u equal g of x. Then the derivative of u with respect to x, du dx, is g prime of x, and we're going to write this in the differential form. Remember that from a while ago? So du is g prime of x dx. It's the differential form of the derivative. And now literally we substitute what I had for u and what I had for du into my original antiderivative. This then becomes f prime of u times du. And now this is just a simple basic antiderivative. It is the derivative of f. And then we make sure you substitute back. We do not want u. We do not care about u. We care about x. And so this is then f of g of x plus c. So you can see it's the reverse of the chain rule. It's called substitution or u substitution. Later on in Calc 2, you'll have something called trig substitution. So generally, we actually ultimately end up calling this u sub. Okay, so let's look at some examples. And this is a little tricky because you have to decide what you are going to pick for u. And ultimately, when you see an antiderivative, or you want to find an antiderivative for a function, you have to decide what method that you are going to use, whether you need to use u substitution or algebra or trig or some combination. It won't be told to you what method that you need to use. So you're going to have to decide. But for the moment, we're going to look at just u sub situations. So as I have x sine of 3x squared minus 1 dx. Now, again, we're thinking in terms of undoing a composition. And so in this case, my u is 3x squared minus 1. Basically, you pick something for u whose derivative is also in the problem. It needs to be something, we need a piece of the integrand to be u, and its derivative, du, also has to be part of the problem. So in this situation, the derivative in differential form is 6x dx. Notice I don't have exactly 6x, but the important part is the variable part has to match. The x dx is in the problem. I can get rid of the 6 by multiplying by 1/6 to both sides. A number is not a problem, but the variable part has to match. Once I have these, I substitute in. This becomes sine of u, doing the first substitution, and x dx is 1/6 du. The number at that point, just stays. When we take the antiderivative, if you like, we can move it on the outside. It doesn't matter. Sometimes I'll just move it directly out. And the antiderivative of sine of u, this is a simple basic antiderivative. Negative cosine of u plus c. Again, I don't want my final result to be in terms of u. I need to put this back in terms of x. And so we get negative 1/6 cosine of 3x squared minus 1 plus c. And this is my antiderivative. If you want to check it, just take the derivative of it and see what happens. You should end with what we started off in the integrand. We're going to do a few different examples. Again, this is an extremely important concept, substitution, and you need to practice these. They are not simple. Seeing what to do is important. Tangent of x. This seems basic, but it is not one of our original basic antiderivatives. What I need to do is write this as sine of x divided by cosine of x. And now I can pick u to be cosine of x. The derivative du is the negative of sine of x dx. And notice that matches. I could not have switched these around because if I had picked u to be sine, du would have been cosine of x. Cosine of x is in the denominator. The dx is really thinking of it in terms of differential, like it's multiplied. That's in the numerator, and that wouldn't have worked. I have to pick u to be cosine of x. The negative of du is sine x dx. I want this to match exactly the part that doesn't have the number, or the variable part. And so then this negative I can just put on the outside, and this becomes 1 over u du. This cosine is in the denominator. When I replace it with u, it goes in the denominator. Sine x dx is du. That's in the numerator if you wish, or in back as multiplication. This then becomes negative natural log absolute value of u plus c, basic form I can find the antiderivative of, which is the negative natural log absolute value of cosine of x plus c. Now, you can use this as the antiderivative. That is not a problem. That's fine. Or algebraically, or trigonometrically, these are the same. This is the same as the natural log absolute value of secant of x plus c. This is what I will use basically as the antiderivative of tangent of x. And this, because it occurs so often, is a new basic antiderivative form. This is the natural log absolute value of secant of x. I can do the same idea for cotangent, and it will work out that this becomes the natural log absolute value of sine of x plus c. U is sine, du is cosine. Just flip, because cotangent is cosine over sine. We can also, using this same process, kind of deal, get the integral of secant of x, and that will come out to be, I'm not going to go through how this occurs, but just the final result, natural log absolute value of secant of x plus tangent of x plus c, and the integral of cosecant of x becomes natural log absolute value of cosecant of x minus cotangent of x plus c. We can also extend arctan, antiderivative, antiderivative that gives us arctan. And if I have the antiderivative of 1 over x squared plus a, where a is greater than 0, this is equal to 1 over the square root of a arctan of x over the square root of a plus c. This last one I am going to derive, and we'll see why that actually works, but I'm going to give you the what it's going to come out to be first. So 1 over x squared plus a is greater than 0. What I'm going to do is, again, you should recognize this is somewhat similar to arctan in the form. Arctan, if it was basic arctan, then a would be 1, but now I want any positive value for a to be there. And so what I'm going to do is factor out an a from the denominator, and that gives me x squared over a plus 1 in the denominator. Or I can write this as 1 over a, 1 over x over the square root of a, quantity squared, plus 1. And now you might recognize that this is ready to do a u sub. If u is x over the square root of a, du, its derivative, again in differential form, would be 1 over the square root of a dx. Or, again, forgetting about the number, putting that on the other side, this square root of a times du is dx. Making this substitution, we get 1 over a, 1 over, on the outside, 1 over u squared plus 1, and then dx was the square root of a times du. This number I can move in and out of the integral sign. That's not a problem. And I get the square root of a divided by a, which is 1 over the square root of a. And hopefully you recognize, that 1 over 1 plus u squared, or u squared plus 1, is arctan of u, the antiderivative. And so finally we get exactly what I said over there. 1 over the square root of a, arctan of x over the square root of a plus c. And you can leave it like that. You don't have to rationalize this and write it as the square root of a over a. I don't care. Okay? A couple more examples. Actually, one more example. Let's suppose that I have, I guess I have enough room, the integral of x square root of x plus 3 dx. And in this case, u is going to be x plus 3. Its derivative du is just plain dx. And notice here, that takes care of what's inside the square root. It takes care of the dx, but I still have left over this x. I cannot write an integral with two different variables. So if I'm going to do a substitution, I have to replace that x also. I can't leave that as x. And so what I'm going to do is say, well, if u is x plus 3, that means x is u minus 3. And so we will use this also. And so now I have three different things to change. This then becomes u minus 3 times the square root of u du. And now, at this point, we can use some algebra. This is the integral of u to the 3/2 minus 3u to the 1/2. And this is a basic antiderivative at this point. So we can go ahead and find the value. This is add 1, take the reciprocal, leave the number, add 1, take the reciprocal, plus c, which gives me then 2/5 u to the 5/2 minus 2 u to the 3/2 plus c. And now I replace, again, don't forget to replace what your value for u is. 2/5 x plus 3 to the 5/2 minus 2 x plus 3 to the 3/2 plus c. And that is my final antiderivative.